In the previous video, we studied the thread synchronization with rlock. We moved to the sixth video of this section, thread synchronization with semaphores. In this video, we'll use the consumer-produced model and initiate the semaphore to 0. We'll then carry out the synchronization process via semaphores. Invented by E. de Kestra and used for the first time in the operating system, a semaphore is an abstract data type managed by the operating system used to synchronize the access by multiple threads to shared resources and data. Essentially, a semaphore is constituted of an internal variable that identifies the number of concurrent accesses to a resource to which it is associated. Also, in the threading module, the operation of a semaphore is based on the two functions acquire parentheses and release parentheses, as explained. 1. Whenever a thread wants to access a resource that is associated with a semaphore, it must invoke the acquire parentheses operation, which decreases the internal variable of the semaphore and allows access to the resource if the value of this variable appears to be non-negative. If the value is negative, the thread would be suspended and the release of the resource by another thread will be placed on hold. 2. Whenever a thread has finished using the data or shared resource, it must release the resource through the release parentheses operation. In this way, the internal variable of semaphore is incremented, and the first waiting thread in the semaphore's queue will have access to the shared resource. Although at first glance the mechanism of semaphores does not present obvious problems, it works properly only if the wait and signal operations are performed in atomic blocks. If not, or if one of the two operations is stopped, this could arise unpleasant situations. Suppose that two threads execute simultaneously. The operation waits on a semaphore, whose internal variable has the value 1. Also assume that after the first thread has the semaphore decremented from 1 to 0, the control goes to the second thread, which decrements the light from 0 to -1 and waits as the negative value of the internal variable. At this point, with the control that returns to the first thread, the semaphore has a negative value and therefore the first thread also waits. Therefore, despite the semaphore having access to a thread, the fact that the wait operation was not performed in atomic terms has led to a solution of the stall. The next code describes the problem, where we have two threads, producer parentheses and consumer parentheses, that share a common resource, which is the item. The task of the producer parentheses is to generate the item, while the consumer parentheses thread's task is to use the item produced. If the item has not yet produced the consumer parentheses thread, it has to wait. As soon as the item is produced, the producer parentheses thread notifies the consumer that the resource should be used. In this example, we use the consumer-producer model to show you the synchronization via semaphores. When the producer creates an item, it releases the semaphore. Also, the consumer acquires it and consumes the shared resource. The synchronization process done via the semaphores is shown in the following code. Initializing a semaphore to 0, we obtain a so-called semaphore event whose sole purpose is to synchronize the computation of two or more threads. Here, a thread must necessarily make use of data or common resources simultaneously. This operation is very similar to that described in the lock mechanism of the lock. The producer method thread creates the item and after that frees the resource by calling this function. The semaphore's release method increments the counter and then notifies the other thread. Similarly, the consumer method acquires the data by this method. If the semaphore's counter is equal to 0, it blocks the conditions acquire method until it gets notified by a different thread. If the semaphore's counter is greater than 0, it decrements the value. Finally, the acquired data is then printed on the standard output. Now let's run the Python file in the command prompt as shown. This is the result that we get after the file runs. A particular use of semaphores is the mutex. A mutex is nothing but a semaphore with an internal variable initialized to the value 1, which allows the realization of mutual exclusion in access to data and resources. Semaphores are still commonly used in programming languages that are multi-threaded. However, using them you can run into situations of deadlock. For example, there is a deadlock situation created when the thread T1 executes a wait on the semaphore S1, while the T2 thread executes a wait on the semaphore S1, and then T1, and then executes a wait on S2 and T2, and then it executes a wait on S1. In this video, we carried out thread synchronization with semaphores. In the next video, we'll see how to carry out thread synchronization with a condition.